Imagine a student, right, not only aces their exams, but starts writing their own textbooks, basically teaching themselves to reach like higher and higher levels of understanding. It sounds kind of sci-fi, right? But that's kind of what's happening right now in the world of AI, specifically with these things called transformers.
Yeah, and these transformer models are already kind of known for being able to do all these complex tasks from, generating text that sounds like a human wrote it to even solving some pretty tricky math problems. But what if they could become their own teachers, constantly pushing the limits of their own knowledge? Well, that's what this research we're diving into is all about.
Okay, so we're talking about AI that can essentially self-improve, right? Kind of bootstrapping itself to like higher and higher levels of capability. That's a pretty big claim. So what kind of evidence are we actually talking about here?
Well, the researchers put these transformer models through a whole bunch of tests, starting with this thing called reverse addition. Now, before you think that sounds way too basic, the point wasn't to, make addition harder. It was to see if simplifying the process itself could actually help the model learn more effectively.
Okay, I'm intrigued. So how do you even simplify addition?
Well, think about how we normally add, right? You start with the ones place, then you carry over to the tens place, and so on. Reverse addition just flips that on its head. It starts with that least significant digit and works backwards. And what this does is it eliminates the need for the model to remember all those carried digits across all the steps. So it can really focus on the core concept of, just adding quantities.
Oh, okay, I see. So it's like learning that essence of addition before dealing with like all the complexities of carrying over. Clever. So did this actually help the model learn?
Yeah, the results were pretty striking. This model, initially trained on averse addition problems with up to 16 digits, it was able to use that self-improvement thing to tackle problems with over 100 digits. That's a huge leap in complexity.
Wow, that's a huge jump. But I'm guessing they didn't just stop at addition, right?
Of course not. They tested a whole range of tasks, including things like copying and reversing strings of characters. Now, those might sound, deceptively simple, but for a transformer model, they're actually like the foundation for how they manipulate language.
So like copying a string is like learning to replicate information accurately. And then reversing it requires like understanding the order and structure of that information.
Precisely. And again, self-improvement let those models handle strings way longer than what they were initially trained on, showed a clear ability to, generalize beyond their starting point.
Okay, so they tackled addition, they played with strings. What other challenges did they throw at these self-improving models?
They even went into the world of multiplication, but with a fascinating twist. It was this thing called chain of thought reasoning.
Chain of thought. Okay, what's that all about?
So instead of just spitting out an answer, the model had to actually show its work step by step, just like, if you were solving a multiplication problem on paper. And this lets the researchers kind of get a glimpse into the model's thought process, seeing how it breaks down all those complex calculations.
So it was like peeking inside the model's brain and seeing like the gears turning. Did they crank up the difficulty here too?
Oh, absolutely. They started with a model trained on multiplication problems up to 5 digits long, and through self-improvement, pushed it to solve 10 by 10 digit multiplications. That's some serious number crunching.
Okay, so I'm seeing a pattern here. Longer numbers, longer strings. Did they test anything that wasn't just about number crunching or manipulating text?
Yeah, this is where it gets really interesting. They challenged the models with solving mazes.
Mazes, like the ones we used to do at kids in those activity books. How does an AI even solve a maze?
Well, the model had to find the shortest path through the maze, showing that it can reason spatially and plan ahead. Not just follow some set of pre-programmed rules.
So it's like testing the model's problem-solving skills in a virtual obstacle course. I'm starting to see why this research is getting so much attention, but I'm still a bit fuzzy on how this self-improvement actually works. Can you like walk me through that process?
Sure, yeah, it's actually a really simple cycle. You start with an initial training phase where the model is given labeled data, up to a certain difficulty level.
Okay, so it's got like a foundation to build upon, like learning the basics of addition before you move on to multiplication. Then what?
Then comes the self-improvement magic. The model gets presented with problems that are just slightly beyond its current training level. Like, let's say being asked to add numbers with one extra digit than it's used to. Now, it'll struggle a bit at first, but it'll try to solve those harder problems, generating its own solutions, which kind of act as new labels.
So the model is like creating its own study guide, learning from its own attempts. Even if they're not perfect at first, that's wild.
Exactly. Then it retrains itself on this expanded data set, absorbing all those new, slightly harder problem solution pairs. And guess what? It becomes capable of handling that higher difficulty level.
It's like leveling up in a video game. You gain experience, learn new skills, and can take on tougher challenges. But wouldn't adding any model-generated data be risky? I mean, what if it makes mistakes and learns from those mistakes? Wouldn't that lead to some sort of like a downward spiral?
That's a great question. And it brings us to this potential danger of what they call error avalanches. If the model makes a mistake and that incorrect solution ends up in the training data, well, it might start learning from its own errors. And that can create this snowball effect, leading to, a collapse in performance.
Yikes. So it's not as simple as just letting the model generate data, willy-nilly. How do they prevent those error avalanches from happening?
Well, they had to get clever, right? They had to introduce some quality control. One method they used is something called length filtering. They noticed that when these models are struggling, they often produce answers that are shorter than the correct solution, almost like they just gave up too early.
Interesting. So by filtering out those like suspiciously short answers, you could weed out a lot of likely errors.
Exactly. Simple but surprisingly effective way to improve the quality of that self-generated data. But they didn't stop there. They also used this technique called majority voting.
Okay, I'm picturing like a panel of AI judges deciding which answers are worthy. How does that work?
Imagine training multiple models all at the same time, each with its own little quirks and biases. Then when it's time to generate that new training data, you only keep the solutions that a majority of those models all agree on.
It's like a democratic process for AI. If most of the models agree on an answer, it's much more likely to be right. Smart.
Yeah, and by combining those filtering techniques, they were able to significantly reduce the risk of those error avalanches happening, allowing the models to safely learn from their own generated data.
Okay, so they've got safeguards in place, but did this self-improvement actually work? What kind of results did they actually see?
Well, the results were pretty remarkable. Across all those tasks they tested, self-improvement consistently let the models generalize, far beyond that initial training data.
So it wasn't just a minor improvement.
Oh, no, not at all. In a lot of cases, the models were able to solve problems that were like orders of magnitude more complex than what they started with.
That's pretty impressive. But what stood out to you as the most interesting finding? What really made you go, wow?
What I found most fascinating was the discovery that self-improvement doesn't just help with, slightly longer sequences or more complex problem. It actually makes the model better at extrapolating.
Extrapolate. What do you mean by that?
Well, it means the models weren't just getting better at those specific tasks. They were actually developing like more sophisticated learning strategies that could be applied to a much wider range of problems. The more rounds of self-improvement they went through, the better they became at learning and generalizing to even harder tasks. It's like they were learning how to learn better.
Okay, now that is mind-blowing. We're talking about AI that's not just getting smarter, but actually becoming more adaptable and efficient at learning itself. This is some serious next-level stuff.
And they even found ways to like accelerate this whole self-improvement process. Instead of just increasing the difficulty one step at a time, they tried presenting the models with problems at multiple difficulty levels, all during the same round.
It's like giving a student a crash course in advanced concepts. Did that work?
Yeah, it did. They found that this accelerated schedule could actually significantly speed up that whole self-improvement process, allowing the models to get to higher levels of performance in fewer training rounds.
That's incredible. It's like unlocking a hidden turbo boost for AI learning. But I imagine there's a risk of like pushing the models too far too fast, right?
Oh, absolutely. There's a delicate balance between challenging the model and overwhelming it. And they found that that balance could change depending on, the task and the model's. Oh, hey there. What's up?
Can you remind me the length generalization? How this work do this? Can we explain the length generalization?
Oh, hey, our listener wants to join in. What's up?
Hey, can we explain the length generalization? How does this work do?
All right, so get this. Imagine a student. Oh, hey there, how can we help? Oh, absolutely. Let's unpack this generalization thing.
Yeah, that's a great question. It's central to this whole topic.
So basically, it's about how well an AI can apply what it learns.
Exactly. It's the difference between. Oh, hey there, what's up?
Okay, so next generation, it sounds like you're asking about how these self-improving AI models could lead to a new era of technology, right?
And that's a really insightful question because this research suggests we're not just talking about incremental improvements, but about a fundamental shift in how AI learns and adapts.
Yeah, it's like imagine the jump from like basic calculators to like supercomputers. We might be at that kind of inflection point with AI right now.
Exactly. And later in the show, we're going to dive into some specific ways that this new kind of AI could impact, areas like healthcare, education, and scientific discovery.
So we'll get into those details soon. But for now, think of this research as laying the groundwork for like a new generation of AI that learns more like humans do.
Yes, a key part of this is that the models aren't just getting better at specific tasks, they're actually learning how to learn better.
It's like they're developing their own learning strategies, becoming more adaptable and efficient, which is, pretty wild.
Now, let's rewind a bit. We were just talking about how these models self-improve by tackling harder and harder problems, right?
Yeah, we were about to get into some of those really specific examples of how they tested that.
So let's jump right back into that and pick up where we left off, exploring some of the actual research itself and the challenges they're faced.
All right, so get this. Imagine a student, right? Not only aces their exams, but starts writing their own textbooks.
Yeah, and these transformer models are already kind of known for being able to do all these complex tasks.
Okay, so we're talking about AI that can essentially self-improve, right? Kind of bootstrapping itself to like higher and higher levels of capability.
Well, the researchers put these transformer models through a whole bunch of tests, starting with this thing called reverse addition.
Okay, I'm intrigued. So how do you even simplify addition?
Well, think about how we normally add, right? Reverse addition just flips that on its head.
Oh, okay, I see. I see. So it's like learning that essence of addition before dealing with like all the complexities of carrying over.
Yeah, the results were pretty striking. This model was able to tackle problems with over 100 digits.
Wow, that's a huge jump. But I'm guessing they didn't just stop at addition, right?
Of course not. They tested a whole range of tasks, including things like copying and reversing strings of characters.
So like copying a string is like learning to replicate information accurately.
Precisely. And again, self-improvement let those models handle strings way longer than what they were initially trained on.
Okay, so they tackled addition, they played with strings. What other challenges did they throw at these self-improving models?
They even went into the world of multiplication, but with a fascinating twist. It was this thing called chain of thought reasoning.
Chain of thought. Okay, what's that all about?
So instead of just spitting out an answer, the model had to actually show its work, step by step.
So it's like peeking inside the model's brain and seeing